close the door.
Yes. Yeah, actually, there was another talk today.
Really?
Your life, yeah. It's unfortunate because I count on people and they commit to giving a lecture, but they also show up and give the lecture. And what's this to that?
One more.
You're giving a class today?
No.
No? Okay. Yeah. Good. So
There's just one person on the file that you sent on the standard.
there was to left sign. Who's to left?
Shit.
I see here somebody that signed up for today.
Ah.
So this is for today. Somebody knows to left is somewhere around or not?
Maybe I'll call him. I don't
Call
know.
him and ask him if he intends to give his lecture today.
Yeah.
Good. Thank you. Good. So today we actually have a talk on fractals, which is the logistic map, special fractal, and on calculation. And we will, hopefully we will get Dulev to come to give his lecture on the Horschel-Koppelmann algorithm to generate calculation clusters. I just want to show a quick update on. So I copied all the material, all the notebooks.
Should I tell him that he gets an F if he doesn't show up?
Yeah, but if he didn't prepare anything, well, do I need to send everybody before the lecture, 1 week before the lecture, to remind them that, this is what they are doing in Kita Gimel. To remind the students that they
Maybe it's
have
just
some
this guy.
assignment. I thought
Maybe you should give him an F.
I thought we should, at university, everybody knows their assignments, right? And they should, when they committed to give the lecture, they should give the lecture at the agreed time. Okay, so, yes, the following. So, we discuss all the time Jupyter notebooks, right? Last week we had the presentation by Eliyahu on iGraph, and what's happening is that before I put everything into a folder on Moodle, but as we saw, it cannot be opened on Moodle. What was you told me about this? What's your name again? Yes,
Dimitri.
Dimitri, yes. So Dimitri pointed this out, that you cannot open a Jupyter notebook on Moodle, and this is why I copied everything on GitHub. So what we have now here is a link to GitHub. See this? Yeah. Okay. GitHub, you click on it, and then you have all the notebooks that you also need when you do later some paper project. You would need some of these notebooks. And the nice thing is now that you can just go to Colab, use Colab, and you say here GitHub, okay? And if you make a link to our repository, then you have all these notebooks here, and you can just open them. So for example, today we talk about the logistic map, so I just open it now, the logistic map. I find this quite nice, comfortable, convenient. So yes, the problem is when you do any changes here, it will not be saved. So you all the time have to go to commit the changes on GitHub. Okay. Good. Any questions about this? Good. Then Joseph, you can talk about the logistic map.
So here is a general picture of the logistic map where you see it extend R from 0 to 4 expanded to a minus. So we will talk it later. This is maybe the whole picture of the logistic map. So first let's see what is the logistic map. It's a discrete dynamical system defined by the quadratic difference equation. There it is. And currently this is a recurrence relation and a polynomial map.
But we have to explain a little bit, not everybody knows what is logistic map. You're experts on logistic map, you know what is xn and xn plus 1.
No, I know what a recursive formula is.
Okay, that's
what it
formula,
is.
But what does it mean? I mean, what does it describe?
I don't know.
Okay, so ask him.
What does it describe?
It's a tutorial, okay? It's a tutorial.
Okay.
He gets his grade by explaining you the logistic map. So don't make him an easy life.
Great.
Okay? Later he won't make you also an easy life. You have to present something.
I hope you will.
Okay, great. So yeah.
So what is the logistic map?
So the logistic map, you just it will be a long term when you understand the whole map. I can tell you this is from the 8 parameters, and this is the x3 what is stable, and you plot all the stable points brought to the parameter, and you got the logistic map and as a flatter picture. And if you want to know exactly, I will tell you step by step. Actually, it's all begin from this little function, and also it shows how easy dynamic system can give us a complex explain of the.
And the x-axis is R on the graph on the bottom.
Yes, but this is the picture from the article which first. No, so first research of the logistic map, so it didn't match. Next I will show you a great more picture of the logistic map. You can change the parameter of it.
But you don't need all this. Go back again. Everybody understood now what is a logistic map? I didn't understand this. I'm sorry.
It's about.
Now you need to start a little bit more basic. Scroll down. Everybody can read this. I cannot read this, but I have very bad eyes. So, Dimitri, you can see this?
Yeah.
Okay, very good.
Oh, sorry.
No, it's okay. It's this is the problem of Jupyter Notebook.
But he can make it a bit bigger.
He can make it bigger? Control, maybe Control plus.
Which control.
Command. Shift plus, let's see.
Maybe in the editor.
It's okay like this?
Yeah, it's better.
It's better?
Yeah.
Good. So what do we see here? We see xn plus 1, okay, is equal to r xn 1 minus xn. Good. What is xn? Xn is, let's talk in the logistic map, can be used in order to simulate the growth of rabbits, for example, okay, or any other animals. But let's stick to the rabbits. Xn is the number of rabbits at today, okay? Today. And you calculate, you want to know what are the number of rabbits next year, okay? So this is xn plus 1. And since they multiply, you have here prefactor r, okay? So it's xn plus 1 is equal to r times the xn that we have today. And what is this term here?
This is the enrollment limit.
Yes. Well, what does it mean for the rabbits?
Because it will not
dying.
They are dying. I mean, they are either dying or they are some fox or wolf or whoever eats rabbits around and they eat the rabbit, right?
So why is it multiplication and not just like minus some other factor times x?
Because it's a kind of a rate. You know, you have this is if you let's say you don't have no death at all, then it's what do we get?
Sure.
Exponential growth, right? So you multiply this in order to to have some kind of to reduce to have some reduction factor.
But wouldn't you just subtract some other constant times xn?
But you have here a subtraction. It's like you have rxn minus rxn squared. Okay?
But why is there a quadratic term?
Why it's quadratic? Very good question. There's actually once I knew it.
Because it's simplest way to describe
yes.
population of growth and dying. So this is the simplest model. So if you want another model, is I can't say.
I had once the argument I just forgot, but there was some reasoning behind that it has to be quadratic because I will tell you next week. Okay? I just
maybe always.
You
can
remember
show
it.
for a minute like the upper part, the full map, like where's the full map? Sorry for coming late. I just want to see. Okay.
So this you will have to understand it because I just thought all the.
Yeah. Okay.
Good.
Just wanted to see.
So what happens now? You have you plug in this equation, right? The xn plus 1 is equal to r xn 1 minus xn. So you do an iteration, right? What you see is after for low growth factor, you will see in the beginning some oscillating behavior, and then it stabilizes. Okay, population stabilizes. So you have only one stable population. This is basically what you see here. If the growth factor is too little, so smaller than 1, they will all die out. Okay, this is 0. So you will see basically a beginning population fluctuates and then it decays to 0. There are more rabbits dying, being eaten than newborn rabbits. Okay, so what happens at 1 when you have a growth? Because I mean, obviously, when you multiply something with smaller than 1, right? You remember the equation. You have there something 0.5 times xn. Of course, it will lead to it's a decaying function. Okay, it will lead to a all the rabbits will be dying. And then what happens at 1 is that you have a stable population. Okay, when you're above 1, you have a stable population, depending on how large. And so here's the population that you will get, right? And the larger r is, the larger will be this stable the stable value, right? So if r is equal to 1.5, you have this more rabbits than if r is only 1.1. Okay, also intuitive, right? So and then you increase until you reach an r of 3. What you get in an r at 3 is that you have your population of rabbits jumps between two values. 1 year it is this value, the next year it is this value. Then it is this value, this value. Okay, it jumps between two stable population points. So this is this bifurcation here.
Yeah, we will see how it changes.
Huh?
Yeah, you will plot it.
You will explain it again. I just want to, if they hear it again from you, it doesn't matter. Just
okay.
That they get basic understanding. Then you continue to 3.3 or something, 3.2, and then suddenly it jumps between 4 points. Okay? you have 4 here. Is understandable? One year you have 1,000 rabbits, the next year you have 2,000 rabbits. Afterwards it jumps down to 500 rabbits. But all the time periodically, okay? It's all the time 4 stable points, so to say. And then you get into a region here where it jumps chaotically. So this is chaos. It's chaotic behavior, okay? Good. So this is
this is how
this is the basics.
Yes.
Are we expecting the chaotic behavior all the time?
The chaotic behavior you get all the time when you are above a certain value of R, which is 3.
I will also show you how to plot
3.3,
this.
3.4, I forgot. Something
Yeah.
about this.
Yeah, actually, the logic map first launched out is for the problem of deducing the climate from the governing equations. It plot also the same equation as we saw here. And then it was popularized in 1978, the paper, so that here are the simple mathematical methods with very complicated dynamics. It's talk about the population growth and use this simple equation to describe it. And he first plot the picture of the logistic map. Okay, so let's start with the example. So the logistic map where X is a variable and R is a parameter. It's a map in the sense that it maps a configuration or face to itself. That is to say the Fs is equal to Rs and 1 minus X. Then we interpret it as a total to get the next position of the configuration space after one time step. So just to give more explain about this point, and which can be iterated as a sequence of time steps in the evolution of the system. We will see it graphically of the picture. We can use it very quickly. This was the initial approach of care to study dynamic systems and ultimately helps starting from the study of the fixed points, or in other words, states that do not change over time. That is to say, to get some abstract points when you set your parameter and the population will change, then it will go to a constant. So
this paper, actually, I recommend you to read by Robert May. This old paper.
This one?
Yes, that's very nice paper and also very intuitive. And what he pushed in this paper, and also later when he gave talks, is that in university we teach this not enough. He said this is a prime example of having a very simple equation. It's a very simple equation, right? This xn plus 1 is equal to rx1 1 minus xn is very simple, but it's so rich. It has a lot of you can from this equation you get the Mandelbrot set. Okay, you can describe a lot of stuff going on in turbulence and convection theory, and you can actually do a whole course on this equation. So here kind of promotes to have at least one lecture on the logistic map during the degree, which I'm doing right now. Or even one could even do more. Okay, good.
Okay, good.
So very nice paper. You should, if you have some time.
Yes. So next we talk about the demographics model example. This is the nonlinear difference equation intended to compute two effects. Reproduction, where the population will increase at a rate proportional to the current population when the population size is small. Starvation, where the growth rate will decrease at a rate proportional to the value obtained by taking the theoretical carrying capacity of the environment less the current population. So that's first.
Good. Another comment. Sorry, I all the time interrupt because I'm so excited. If you look at the equation and you can also write it into to a differential form, and then you have a first order differential equation. And what kind of first order differential equation is this?
Non-linear.
Yeah, and from all the mother we learned in the first year, which kind is it? From the nonlinear?
Maybe
Sure,
it's
yes,
exponential.
It's Bernoulli maybe?
No, but you get an exponential solution, but if you would solve it, what?
It's maybe Bernoulli.
Aha, yeah, it's Bernoulli. Right.
And I know that if you do it complex, so you get like the Mandelbaum set like
Exactly,
this.
exactly, yeah.
It's
So
very
if you-
cool.
Yeah.
It's again on the Mandelbaum set.
So basically, when
Yeah,
you
can I see?
when you turn by 90
If you can
degrees,
open it later,
Yeah, I
it's,
can.
it's
I can.
very beautiful.
We will talk about that at the end.
Okay, sorry to.
No, no,
It's okay, it's okay.
So this was the Bernoulli. So if you want to solve this equation, you use this Bernoulli ansatz that we studied in the first year. Good. Next.
So first is the characterization of the logistic map. So we just plot the logistic map theory as if to how I change the parameter and how you see this is the indentation of n that we see how you calculate it again and again. So if you have R to 002, it will close to the 0 constant.
So you have 0.3. The population of rabbits is 0.3 at the beginning, and then it dies out, right? Because your R is so small. That's what you're saying.
What is
It takes time.
Yeah, so now you can see it converts to a no zero constant about this.
Yes.
So
Because you are above 1. Right?
yeah, so let us plot a g for this that will say if change. I will change the r to the time, and you will see how it changes about this. So first is convert to 0, then it convert to a constant, then it will give you a 2 stable point. Yeah. Here the upper is the first one and the lower is the second one stable point. Then it occurs a coils. That's it how it changes. So let's see the characters of this logistic map. So the exponential converts to 0, or it converts to a non-zero fixed value, then initial oscillation, then converge. A stable oscillation between two values. Growing oscillations between a set of values which are multiples of 2. That is to say, first the population will be 2, then your stable point will be 4, then your stable point will be 8. Then instantaneously, fully developed chaotic oscillations. Then the topological mixing. Then that is to say, you got you may get a chaotic, but at some point you will get a stable point. Well, I will explain it carefully about this. Actually, if you this direction on how it changed about R is very close to the turbulence. For also the turbulence, you just you set a stake on the window of the water, and the water flow isn't so fast. It will just stake 2 flights, and if you set the water run very quick, it will give you a random and oscillation. Maybe it will get a chaotic, like what we see in the logistic map.
So this is water streaming inside another water
give a stick here and
A stick?
set the water run to push it. Yeah,
So where's the stick there?
here.
That's there.
Yeah, stay there.
And red is when you don't have no water. Or what is?
Oh, this is a picture I grabbed from the web. So this here is a stable map and
So the pen is like you put now.
yeah,
The pen is like this. Okay.
yes.
Good. So you have the most turbulence you have directly after the pen. Makes sense.
The heat map represents velocity.
Flow.
The flow.
Oscillations.
Yeah.
It's flow. Yes.
Yeah.
Okay.
So let's talk about the domain graph and the fixed points. First, you can see we graph the xn plus 1 to vs the xn, and you plot the x plus 1 equals to xn. So here you have two stable points. First is 0. That will say if you put xn to 0 and xn plus 1 will be 0, and so on and so on, all the x will be 0. Or you get this point. So xn equals to x plus 1. So if you go to this point, also the x1 will be this value also for xn plus 1 and so on and so on. This is another stable point. Okay, all these points is all these points you sum of all of this is the graph we see here. So understand some of this. So these fixed points also count the invariant points. So here we drop fx equals to x to find the stable points, and so we now can solve in for the stable points. There are two solutions. First is x equals 0 or x equals to r minus 1 to r. Another graphic technique that can be used on one wasteful mapping is sticker web projection, spider web projection. After determining an initial value on the original x-rays, the following steps: first, draw a vertical line from the initial value x-ray to the curve of x-axis. Here to see here. First, you get this, and how you know the xn? You just net this to fit the plot of our function. Then you plot to this. Here is to say the x minus x plus n plus 1 equals to here now become xn. Then you find the function of the x n plus 1 to xn. Then you get another x minus xn plus 1 when you calculate again. Then again and again you get the spider plot.
This is graphically representing this iteration.
Yes. So first from the iteration of the 59 row and another vertical line down to the curve, and then repeat this process. This is how it is true. By continuing a sequence, spider web or a system-like diagram is created on the plan. This conclusion is pertinent to graphically completing the trajectory, and the spider web diagram represents the trajectory starting from x0. You see, yeah, this is r equals 0.5 and the x3 from 0 to 1. You can see it is very step by step is close to the stable point. If we change it to a smaller one, oh, that's cool. Yeah, I set it.
You have to go above 1. That it goes over this dash line.
Yeah, below 1 it will just go to 0.
Yeah, remember, you need to cross the dashed line, right? And what is this? So
Yes.
put there 1.1 for R. Yes.
Yeah.
It's
guarantees that this line method will converge on the stable point?
Well, pardon please. What?
What guarantees that this method of going to the value and then going to the new x, etc., will converge on the stable point?
You can. It's just a graph picture of what we just.
All of the iterations.
Yeah, we have just no. You just here is the 50 steps, and we here draw 50 steps.
But you can still answer his question. What guarantees this?
Because
That it converges to the stable point. This graphical method.
yeah, because you calculate it will converge. It's a property of the logistical map.
Yeah, but the answer is there's no guarantee because sometimes it doesn't converge. When you're for an R in the chaotic regime, you don't find a stable point. Then
But when there is a stable point.
Hmm?
But when there is a stable point.
when the stable point,
Yes.
then just this projecting back and forth. There's actually a theory in math that shows that they use this a lot. And when you look at the, this YouTuber, how's it called?
3 blue, 1 brown.
Yeah, right. So he uses this a lot for all kinds of different. You remember he had this two cubes colliding with each
Yeah,
other in the wall. He also uses this
Right.
graphical representation. They use it a lot in math.
Can you put more steps?
Hmm?
Can you put more steps just to see what happens?
It's
It's a custom.
just a reach the point you can create another one.
But if you would put now choose an R in the chaotic regime,
Yeah, like
because we want to see how it does not reach stable point.
Does not reach
Yeah, we use 3.5. I don't know.
I think it's
3.5 you had before. No, 5 is not good. Okay, 5 is
yeah.
nothing
You
above
don't reach
4.
this. Oh,
No, maybe 3.8. Ah, here.
wow, still
Okay.
reach.
yeah.
Good.
It's beautiful.
But it did reach it, no?
Yeah, yeah.
No, it just
No,
stopped
it's
there after 50 iterations. So
Ah,
if you put now 100, it continues. Put 60, not 1. Or put 100.
Yeah. Put 100.
Yes.
Yeah.
See, I mean, it stops somewhere, but it's not stable.
No, but it still reaches, not? No, it's like
No,
It's
it is.
but it
Oh,
reaches it and then like
Yeah, but if
Goes
you
up.
would
like
continue,
goes
it
up.
goes,
Okay.
goes again
So
up.
we don't know where it stops. Like.
Yes, you don't know the trend to it convert to just one point. It's just
Yeah,
caps.
everything. Yeah,
Yeah.
it's very good.
Okay, let's see the here dependent on R. So the image below shows the aptitude and the frequency content of a logistic map that integrates itself of parameter values ranging from 2 to 4. So you see how the aptitude of R we just see in the picture, and how it influences the frequency spectrum.
But
So-
we didn't see much. You explain this now?
Yeah.
Okay.
So this is shows how the logistic map from one phase space to affect another phase place to makes the first makes the chaos to spread from the Xn and Ri space to the frequency spectrum FFT space.
Okay.
Then we talk about the case when R smaller than 1 and bigger than 0. At this point, as you see, the population are dying, so Xn decrease multiply for any value of X0 between 0 and 1, and that is the Xn converges to 0 in the limit of n go to infinity. The point at which Xn converges is the fixed point as star fixed points of this map, and where objects around them converge are all called as many asymptotically stable or attractive. So conversely, if objects around x move away from x as time n increase, the fixed point is called the unstable or rich set. So what we just plot is just the stable point. Now here I showed the r is smaller than 1 and bigger than 0. It will convert to the 0 point, stable point. The common and simple way to know whether a fixed stable is small
Asymptotic. But
yeah.
everybody knows what is asymptotically, right?
Yeah. Okay.
It's just difficult to say.
Yeah. Actually, we just say stable.
What is the info?
Yeah.
Asymptotic.
Yeah. So this theorem is expressed as f dot. So a fixed point is stable if the following condition is satisfied. So we take the derivative of it, and however, the discrimination method using the equation does not determine the range of objects from xf, but actually we take now the x0 from 0 to 1, so this method will help us to see if it's a stable point. So in the case when r is bigger than 1, smaller than 2, so the population will quickly approach the value of r minus 1 to r, independent of the initial population. And when r is equal to 1, well, the curve is canted to the 55 diagonal to the x equals to 0. In this case, the fixed point in which the exercise is negative range for 0 minus for r bigger than 0 or and smaller than 1 is x equals to 1. Is x equals to 0. So for x equals to 0, all the stable equals to approaches to 0. So just r equals to 1, the x collides with x equals to 0. The collides give rise to the phenomenon known as a transcriptional bifurcation. That's it how we see in the. That's it how we see here. It grows to 2 stable points. So next we will talk about in case when r is bigger than 2 and smaller than 3. So in this case, the conversion is not monotonic, and it's available to approach f2 to it becomes larger and smaller than f2 rapidly, and follows a converge strategy to oscillate it around xf2. As we see how it changes here. When it's around 2, it's bigger than 2 and smaller than 3. It will just give you the 2 results and then oscillate it around a single constant. So in the case when r is bigger than 3 and smaller than 3.44949, it's a very stable. It's a very interesting step now. So for r equals to 3, a type of bifurcation known as parallel doubling bifurcation occurs. Just as I just showed you the bifurcation convert to 2 dots. And for r bigger than 3, the orbit no longer converges to a single point, but instead alternates between large and small values even after a significant amount of time has passed. That is how to see it change from big to small, then to small to big, over and over again. Okay, these two values are depend on r and are given by this function. Leading a straight line. Then an orbit that curves through the same values paradoxically is called a periodic orbit. In this case, the final behavior of the variable set n goes to infinity is a periodic orbit Yeah, here is what we show of the xn plus 2 and xn. You can see 0 applies the 3 stable points of this. And then the case when r is bigger than 3.44949 and smaller than the 3.56985. As r creates the periodic W bifurcations occur differently, as it's from 16 to 32 to 64, and so on. An infinite pair that we see the orbit never returns to a single value. It's infinite of pair W bifurcations is called a cascade. So let's just say when the length of the bifurcation point in R denoted at RK, when it goes to infinite, the R equals to the 3.5966. That will say when we got the stable point, we will just now stop here before the chaos occurred. The exactly point is 3.56994. So furthermore, a rate of the case of RK reaches a constant value in its limit. What is we call the Feigenbaum constant. That is how explain why the logistic map is a fractal. Because if you look at the let me change it for you to see. Let's see from 2. Yeah, if you see the ratio between this, and you zoom in, you find the ratio. You find the ratio between this and this smaller one. It's a constant called Feigenbaum constant. It's 4.669. So that explains why the logistic map is a fractal picture.
So everybody understood the Feigenbaum constant, right? Just to look at when we have these bifurcations and we just put always the durations from one kind of bifurcation to the other. And you put the ratio, and the ratio is always constant. Feigenbaum discovered this, and the interesting thing is it's a constant that doesn't appear nowhere else in nature. I mean, logistic map appears in many different areas, but the Feigenbaum constant only appears in
we can see another other types of the produce function, and we can use a quadratic method to simulate the functions, and we can how to say the to make a quadratic function to to get the same value of the different types of the logistic map. Then the ratio is always a Feigenbaum constant.
Yes. Yes. So you mean you do now we have a logistic map defined as
here. Yeah.
You put with the sinus. Okay.
Yes.
So you put the sinus. Before we had Rx 1 minus x, right? And now instead of this, you write as a logistic map B sinus alpha xn.
Yeah.
Okay. You get something that looks similar than our old logistic map, also with these bifurcations, and the ratio of the times it takes to get from one kind of bifurcation to another one is the same as in all logistic maps that you reconstruct. So it's very interesting. It's universal.
Yeah.
Yes.
Like the constant, right? Like the
Yeah, it's a constant. It's a constant that
and no one knows why. It's
a mystery.
Yeah.
It happens in all these logistic maps, but nobody knows why.
Yeah.
hear you.
Yeah,
Please,
I just talk about.
You talk to yourself. Okay.
Yeah, okay. Cause I think this we already know in the fabrical class, and this you may very familiar with fabric dimension of the Feigenbaum attractor. Do you still know how to call this?
Now, what is the Feigenbaum attractor? Can you explain?
What?
The Feigenbaum attractor. You talked about the Feigenbaum.
The fractal dimension.
Yes, but you talked about the Feigenbaum constant before.
Yes.
Now you talk about the Feigenbaum attractor. You see the first people already leaving your lecture.
The Feigenbaum attractor is a region that has the property to attracting surrounding objects. That is, say, at this point, if you want to plot another.
I'm not sure you can go above 4.
Not above 4. I think it's above 4. Yeah.
Whoa.
So you see, the attractive point is where if the initial point you will cross coils before you get the stable point of the fractal attractor, and when you be catched by the structure, your x and your x is converted to a constant. That's why it's the attractor of this.
Okay.
And structure of the fractal attractor is same as the fractal feature called counter set. That is how I show here. You see the
What is the counter set?
yeah, it's to create a counter set is it's a more complex function, and I just give you the picture of this. Actually, I don't zoom in the function of how to create a counter set.
But how do you get from the logistic map to the counter set?
You just use the property where the attractor, the probability where the attractor will apply. Yeah, here. So, this quality of the parameter. So when you cross in a cause, the unpredictably apparent randomness leads the logical equation to use the classical map number generator in many. This is how it's used. So this function is plot where you can get the most of the vibration fiber attractors. You see, if you around 0 and 1, they are most of them. You can see from the darkness of our plot. You can see around the 0.5 is very light, and around 1 and 0 is very dark. That is how you know you get the vibrator fiber attractor from the counter set. I should give you the generate function of the counter set. It just you see it has 3 part of this and then 3 part of this and this 3 part of this, so again and again. So next is the fabrical dimension of the Feigenbaum attractor. So we may all familiar with the fractal dimension. Do you remember this? How you see if the shape of if the shape is so a line is 1 dimension, and what about cubic?
my lecture next week is about calculating fractal dimension.
Okay.
So maybe I'll go over that.
Okay, so you can.
But everybody remembers how we calculate the fractal
Yeah.
dimension of a Koch curve, right? We looked how
Yeah.
the scale of we said that we take a ruler and we measure the length of the Koch curve, and depending on the length of the ruler, longer ruler length, shorter length, right, of the Koch curve, and the more you go into details, the more you longer is your Koch curve. And how this scales is the dimension, fractal dimension. Right?
Remember, it's a log
By
ratio.
log plot, you get a straight line. Yes. And you will talk next week about box counting. Right?
About what?
Box counting?
Yeah, it's the same method, just in.
Yes.
Yeah, good. So next is the case when r is equal to this number and r is bigger than this number and smaller than 4. 4 is the end of our story because when you set the x to from 0 to 1, the biggest number is you can get r is 4. So as r equals to 3.5699, it's the onlys of curves marking the end of the periodic doubling cascade. So for almost all initial conditions, we no longer obstructive oscillations from finite period. So it's just slight vibrations in the initial population, yet dramatically different results over time, prime characteristic of caps. So development of chaotic behavior of logistic sequence as a parameter R varies from approximately 3.56 and to approximately 3.82. It's sometimes called a Pominium Manu with Pominium signal. It's characterized by a periodic phase interpreted by brushes of a periodic behavior. That is, say, when you face the chaos at some time, then you crush a stable point where you get some stable x, and then you zoom in also the chaos, then you get another stable point. This is how something used in the semiconductor. Here you let the electrons to go, and here you stop them.
How would you use this in semiconductors? I understand
No, it
you
just
construct a device like this. That
I think it's to show more. So what I learned is you make an insulator to give a group frequency of you make a insulator to and group and give a frequency to hit the solid. Then you group the frequency of your insulator, and it will show a logical map picture of the so it's just how you insulate your solid and how you change your frequency to insulate it, and how it can let the electrons to go and sometimes not. first one to do it is use a liquid. That's, yeah, you see it's a video. You remember?
It's what? Bro?
A video. You show me. On YouTube, a cubic box, and you heat a half is hot, half is cold, and you change the frequency to heat it, and it will show a logistical map of the temperature.
Ah, okay.
Yeah.
Yes.
Also for the semiconductor, it will show a logistical map of the some quantum parameters, and at some point it's just stop the electrons, but at some point when it get a coils, it will let electrons to go.
Okay, good.
Yeah. Also, so this is for the when coils occur. So this is for the first measure point of the logic map. Beyond, so after 4, almost all the initial values eventually leave in virtual 0 and 1 and the word. So this is the end of the logistic map. But now we can talk precisely of the matter where when the r equals to 4 and r bigger than 4, we extend it to a more complex way. When parameter equals to 1, the period comes out over the entire range of 0 to 1, and the initial measure of the density of points rho can be also given by the exact function of r equals to 4. That is how the frequent attractors distribution on the r equals to 4. When r bigger than 4, it will show you this. You can see your values from 0 to 1. You set it, and the xn will go to infinity or finity. So there will never be a stable point of it. That's the point of what we need to know. And next is when r is smaller than 0. Also, we can plot it as stable approaches as a fixed point of f equals 0, but when a exceeds -1, it shows also left trace into 2 periodic points, and what we see in the when r is bigger than 1. So that's how the characteristics of it. And here our mathematicians have done some very precise solutions to Sn to S0 when r equals to some exactly value. This also helps us. I don't know how they apply them to some devices or something, but I think it's very useful when you can grab the picture from what we see here. When you can get the solution from what we see here, when you can know when is the stable point and how it will grow with your x0. And we talk about the coils and the logistical map. So the content of coils is first a great sensitivity to initial conditions, the topological transitivity, and dense periodic orbits. A small error in the supposed initial state of the system will tend to correspond to a large error later in the evolution. So there's no precise and crucial definition of the chaos, but we can know it's just the similar is just a very, very massive. Here we plot it to how we know some information in
it's only pseudo-random numbers?
Because you can predict it. It's just
Because it's
very
deterministic, right?
yeah.
What is a better way to generate random numbers? Really
Quantum
random
mechanics.
numbers?
Quantum mechanics.
It's always a good answer. Yeah, it's kind of quantum mechanics. Yeah, but okay, how in quantum mechanics? What do you do in quantum
Like
mechanics?
seeing some random process, like the decay time of some atom or
Yeah,
something.
I remember.
Yeah, so nuclear decay
Yeah.
is a nice way to. So this is actually when people need really random numbers, then they use nuclear decay because this is really random. Okay, so that is pseudo because it's deterministic, so to say. Yeah. Okay.
Next is about the university. We just talk about way to see when we have another type of the geodesic map, but we got the same figuration construct. Also, if you use a quadratic formula to fit your produce function, as we add a parameter of alpha, it will also get another constant. This is the first constant and this is the second constant. So at first you see, so why we use a quadratic formula? Because only the quadratic formula we can graph the logistic map. And even if we use a different logistic map produce function, we also use a quadratic function to make the same relation of the produce function. So next is how we see at the beginning describe the population model. Here is the function where we at the beginning of the article there is here this article here in this article we talk about how to describe the population, and the exact formula is here. Here is the population you get next, and here is the population now. If you set xn as this formula, you will get exactly logistic map produce function. Then you can set it to a time-dependent function and got the xn as a function of delta t and n. Here you can know where the delta. If you set the delta t to very small, you can step by step plot how xn exactly is. And then is the picture where you show me. Yeah, at the beginning. Here is how this picture plot. The z and c are all the complex number, and you just calculate the z n plus 1 again and again. Then if the c don't divert to infinity, you put the point on the picture. Then you can see around 0 is very large region, and so beyond 0 to infinity, there are no numbers that face the limits to make C a finite number. And now we put in another Robin set, just each desk in the diagram corresponds to the region of the stable periodic orbits of a center period. By just posing the logistic map orbit diagram with the another Robin set diagram, it is possible to see that the stable fixed points period doubling bifurcations and the here is 3 windows of the logic map. Object diagram correspond to the real axis to the non-rod set diagram. Here you can see the start point and the vibration point, also again and again. Yeah, that's all of my.
So everybody understood what is happening in the first big part of the Mandelbrot. Mandelbrot, did we talk about it actually? I think
the factor lecture, I think.
yeah, I talked briefly.
You always talk about the.
Yes. So what? I mean, you get all of this when you just do iterations, right? And when you have something that converges to a stable point, you put it in black, right? You just color it in black, and everything that is not, that diverges, you don't put in black. Okay, so this is the whole complex plane. And now, when you have a convergence to a single value, this is all what you see here. Okay, all this big body is when it converges to a single value. S in the logistic map, right? We had also here convergence to a single value, single population of rabbits, right? And then you had here this bifurcation, that it goes onto 2 stable populations, and this corresponds to this body of the Mandelbrot set, and this is another one. So it's like when you turn the Mandelbrot set by 90 degrees, you see the logistic map. It's very interesting. Okay. And another thing, logistic map is when you look at a dropping tab, Paris. Okay? When it's not closed completely, it makes it drop, right, periodically. And then, if you would open a little bit the flow, what you would see is that the drops come out in pairs. Okay? So the drop is basically on this regime, right? And then, if you increase the flow a little bit, you have a period doubling. They come together. 2 drops, a pause. 2 drops, a pause. And then you can really increase a little bit more the flow, and then you get again a period doubling, right? And you can even simulate the chaotic regime. If you can picture it with on the telephone, you have this slow motion thing. You can picture it there and see the chaotic how you get in this chaotic regime. It's very interesting. So logistic map is very rich, and can see it in a lot of natural phenomena. Okay, thank you. Good. So no lecture today on